So let's revisit a problem we've done before. So we had mass moving along at some velocity v naught. Let's say this is 2.34 meters per second. It's sliding along a rough surface, so mu sub k 0.317. And I want to know how far does it go until it stops. Well, we've already done this problem, so we know that x is going to be v naught t plus 1/2 at squared. We know that the final velocity is 0, that's just v naught plus at. Okay, so t is minus v naught over a. I plug into this equation over here, and after a little bit of algebra, I get minus v naught squared over 2a. Nothing is different from what we did before. We say, okay, free body diagram, we've got the normal force, we got mg, we got the kinetic friction, we know it's moving in this direction to the right, so that means that the f sub k is going to be negative. So we know that ma equals minus f sub k. We know that f sub k is going to be mu sub k mg. So a is going to be minus mu sub k times g. So x is minus v naught squared divided by 2 mu sub k g, and the minus 2 minuses make plus. Okay, so if we plug in the numbers, notice the mass cancels. So we plug in the numbers and we get 0.880 meters. Okay, so we've done that problem. Let's do a different problem. Let's say that we are now sliding up an incline of 25 degrees. So V naught is still going to be 2.34 meters per second. Mu sub k is still going to be 0.317. Okay, so well, you look at it, and if I make this my x-axis right here, okay, then x equals, well, everything's the same as before. So, we have the same equation, v naught t plus 1/2 at squared, 0 equals v naught plus at. So x is still going to be equal to minus v naught squared over 2a. That part has not changed. And so we look at it, so all we got to do is find a. Well, free body diagram, we've got mg like this, we've got the normal force, we've got the kinetic friction. We know that direction is going to be the x-axis, so I'm going to say that way is positive. Okay, so that means that net force equals ma. So ma is going to be equal to minus mg sine theta, that's going to be this component right here, minus mu sub k times the normal. The normal in this case is mg cosine theta. So the m's all cancel. And so a is going to be minus g times sine theta minus mu sub k cosine theta. Okay, so we plug in the numbers, 25 degrees and mu sub k and g, and we get that the acceleration is minus 6.98 meters per second squared. Okay, so the x up here is just like before. All we have to do is plug in. So minus v naught squared, 2.34 meter per second squared, divided by 2 times a negative 6.96 meter per second squared. And so x comes out to be 0.393 meters. Okay, so when it was going straight, it was able to go a distance of 0.880 meters, going up an incline, it can't go as far. Well, of course not, because gravity was pulling against it. So now we say, what about going down an incline? So now let's say we go down an incline here, and let's say this is 11 degrees below horizontal. Okay, so same as before, the x is still going to be minus v naught squared over 2a. That hasn't changed. And so now, free body diagram, we have mg, we have the normal force, we have friction like this. Okay, I say that direction's positive, x, so that means that net force is mg sine theta minus mu sub k times the normal. The normal is going to be mg cosine theta, and that's going to equal ma. So the m's cancel. So the acceleration is going to be g times sine theta minus mu sub k cosine theta. Okay, we plug in the numbers, and a comes out to be 2.32 meters. So going down the incline is vastly more distance. Gravity's pulling you down the incline, friction slowing you, but gravity's trying to pull you down the incline, so it takes longer to stop going down the incline than it does going level. It takes less distance to stop going up the incline. Well, now let's make it steeper. Now say 25 degrees, because I made it 25 degrees before, right? And so you look at this and say, well, what's different? Well, x is still minus v naught squared over 2a, okay? And just like before, same free body diagram, so that means that we end up with pretty much the same thing. We have mg minus mu sub k, mg sine theta minus mu sub k mg cosine theta equals ma. So the m's cancel. And so a equals g sine theta minus mu sub k cosine theta. If I plug in all the numbers, I come up with 1.33 meter per second squared. Okay, now here's a problem. Up here in my x equation, if you remember how we derived that, we assumed that v equals v naught plus at, and we assumed that was 0. V naught is a positive number, so we're assuming that a is negative. This a is not negative. What does that mean? It means at an angle of 25 degrees down, it is accelerating. So it's going faster and faster and faster. It is not stopping. So it never stops. There is no stopping distance at all. In fact, it speeds up as it slides down the incline. So we knew that when it was 11 degrees, it stopped way down the incline. We know that when it's 25 degrees, it never stops. In fact, it's speeding up the entire time. So what I want to know is, what is this critical angle at which it doesn't stop? So the maximum angle it can move so that it doesn't stop. And we say, well, okay, so the critical thing was when the angle was 11 degrees, the acceleration was negative. When the angle was 25 degrees, the acceleration was positive, greater than 0. So clearly, at the critical angle, the acceleration has to be equal to 0. Okay, so we know the acceleration, okay, the acceleration was given by g sine theta minus mu sub k cosine theta times g. So we can cancel out the g's, and we do a little algebra here, and we find that mu sub k equals the sine theta over cosine theta, so that's tangent theta. So that means theta, the critical angle here, is going to be given by the arctangent of mu sub k. So that would be the arctangent of 0.317. So that comes out to be 17.6 degrees. At 17.6 degrees, this is this critical angle. At that angle, it will never stop. It will keep sliding forever and ever and ever, but it will not speed up and it will not slow down. If it's a lesser angle, it will eventually slow down and stop. If it's a greater angle, it will keep speeding up as it slides down. So that's how you do this thing, sliding up and down